Guys, we'll solve a small numerical on the Euler's formula. So Euler's formula was made around 300 years back, and it's still being used for long columns. And you know that last time we explained the crippling load for a column. The crippling load for a column could be depending upon the end conditions here. So it could be hinged like this, it could be hinged, it could be fixed, it could be fixed like this, it could be hinged and fixed, it could be hinged and fixed like this. Sorry, here it almost goes like this. And it could be one end fixed, the other end free. Guys, we are shown like this. This would bend like this. This would almost bend like this. This would actually take, this point of inflection is slightly larger. So something like this. So all this would actually bend like this. So these are actually the bending of this. Now this Euler crippling formula, this Euler buckling formula or the crippling formula is given by these two this pi square E, this is constant, this is actually I minimum. So I minimum refers to the least moment of inertia. When I say I minimum, least moment of inertia. So that is least moment of area moment of inertia. So you know that if there is any column like this, if you apply load, then, okay, I said last time with the example of a scale, that is I'm measuring scale. So this column would actually try to bend in this way. This will not try to bend about this axis. It will try to bend about the least moment of inertia. So that we have to know. And then if you know the effective length, then we can calculate. Now, I want you to use your common sense and actually guess. Suppose if you had a metal rod, okay, almost the size of this pen, what do you think is the diameter of this pen? 2.5 centimeter. 5 centimeters this much. So I like 1 plus centimeter, maybe 1.5. Now if you had a rod almost the size of this phone stand. Okay, can I stand on this? So can I stand on this without this rod getting buckled? You feel it will buckle? You feel this solid rod, not a hollow rod like this. Now you may say what condition it is. Now what condition is it? Now will you say whether that rod is actually hinged like this, whether that rod is actually fixed on both the ends like this, whether the rod is fixed at one end and hinged at the other end, something like this you should have asked. Okay, so it also depends on this end conditions. Imagine this is hinged, that is hinged in both the conditions. I feel I can stand because this will not allow this to move to the sidewards. It is actually bound. This will actually maintain the axis. In all the cases, it will maintain the axis. Only in this case, the axis doesn't get maintained because it is free at one end, it starts moving to the other end. Okay? Now this, we have already seen that this LE, effective length, for this case, LE is equal to what? Do you remember, guys? LE is equal to the actual length of the column. If this is 1 meter, then effective length is 1 meter. If it is fixed at both the ends, LE, effective length is half of the actual length. And in this case, where it is fixed at one end and hinged at the other end, LE is equal to effective length is equal to, it is not half, it is slightly greater than half. So it is L by root 2. It is not divided by 2, it is divided by 1.14, which means this is larger. Okay, in this case, the point of inflection almost comes like this. So LE becomes equal to 2. LE is actually 2 times of the actual length. So we'll now try to solve a problem. Guys, okay, I'm asking you to solve a problem now. A rod of 1.5 centimeter, 1 meter length, hinged at both ends, and this rod is steel. This is made up of steel, which has got a Young's modulus of 200 GPa. So 200 GPa. Find Euler's crippling load. Find Euler's crippling load. Okay. Okay, now we will see this formula. PCR is equal to pi square I by L square. Now, for this condition, a rod of 1.5 centimeter. 1.5 centimeter is 15 mm. So let us try to find each of this one by one. I know this 2, Young's modulus is already given. So 200 GPa is nothing but 200 Newton per mm square. Is it right? Is it right? What right, man? So 200 G stands for 10 to the power of 9. Pascal stands for Newton to the power of meter square. So here this becomes 200 into 10 to the power of 3 into 10 to the power of 6 Newton per meter is millimeter. 10 to the power of 3 millimeter. 10 to the power of 3 millimeter. Is it going out of the view? Huh? Okay, 10 to the power of 3 millimeter. Okay, so this is actually 10 to the power of 3 millimeter to the power of, square it is. So it cancels out. So this is 200 into 10 to the power of 3. This 10 to the power of 3, this 10 to the power of 3 cancels out, and you are left with this. Okay, guys, please do the units. There are already a lot of idiots in India. So please, there are a lot of engineers who are not fit to be engineers. Please don't make some small mistakes like this. So it is 200 into 10 to the power of 3 Newton per mm square. 1 MPa is equal to 1 Newton per mm square. That's okay. Okay. Now we know this Young's modulus. Let us find I minimum. Let us find I minimum here. So I minimum. So moment of inertia for a circular rod. Now thankfully. Hey, hello. Can't you keep quiet? Guys, this in the case of the circular rods, whether it is IXX or whether it is IYY, it makes no difference. What is I for the circular sections? What is the formula for I for circular sections? What is the formula? It is the same. Whether it is IXX, whether it is IYY, it is same because it has got the same resistance to bending in both the directions. So I minimum is the same. Suppose if it was actually some rod like this, suppose if it was actually a rectangular rod like this, then it was like a scale. If you bend, the scale tries to bend towards the least resistance path, that is this. It would try to bend about this path, but it wouldn't bend about this YY path. Okay, it can't bend about this, but it will bend about this. So you can actually find out I minimum. But in this case, since it is said it is a rod of 1.5 centimeter, so I is known, so I is same. So I minimum is same 5 to the power of 4 divided by 32. So what is the formula?
So it's actually 64. 5 to the power of 4.
Sorry, I made a mistake. That was JP.
Yes, sir.
So that was JP. So this is 64. That was 64. Okay. So here pi into d to the power of 4. So how much is d? 15m square divided by 64. So what's the answer? You get some answer. Okay. You get some answer. So we can substitute this later. And then, guys, somebody calculate this mm to the power of 4. Sorry, mm. So this is not square, this is raised to the power of 4. Okay. Now, PCR is equal to pi square. So, you are now trying to find out this values here. LE is equal to how much? LE is equal to, okay, which condition is it given? Hinged at both ends. So that means LE is equal to the actual length. So how much is the actual length? 1 meter length. So 1 meter length means LE is equal to 1 meter. LE is equal to the actual length 1L. So it is actually 1 meter. 1 meter is 1000 mm. 1 meter is 1000 mm. So here PCR is equal to pi square EI. So pi square E is 200 into 10 to the power of 3 Newton per mm square multiplied by I. So I think is it going out of this? Okay, it's no, it's visible. Okay. So I minimum. So how much is actually, so much is this value, guys? 2485. Okay, I think that's enough. 2485 millimeter to the power of 4 I minimum divided by L square. So LE is 1000. So that is 1000 mm square. Guys, basically you said a rod of this size, rod of this pen size, which is actually 1.5 centimeter, if it is 1 meter length, it can take my load. Imagine I'm around like 80 kgs. So 80 kgs is 800 Newton. I should get the answer which is actually more than, I mean around 800 Newton. I feel that these rods, when they are hinged, it's not easy to buckle them because these are quite, 1 meter is not a very big length. I feel so. So let us see what the answer comes. It should be in that range. We have a feel of this rods bending, no? So with that feel I'm going. So much is the answer you got, guys? Huh? 4905.19 newtons. Guys, here you can see here it is millimeter square, here it gets cancelled, and here it is millimeter square, it gets cancelled. So what is left is only newtons. Guys, you can see this is like 4900 newtons, which is around almost 490 kgs. If it is hinged at both the ends, it is able to take a load of around 490 kgs. Now, suppose if it was free like this, suppose if it was like this stand, on one end of the stand you have got the phone now, which is free to move because there is no constraint here. So in all these cases there is constraint. There is some way of trying to hold this from not actually moving to the sidewards. So here you can say that okay, it has taken so much of load. Suppose if it was actually free at one end, all the data is same. A rod of 1.5 centimeter diameter. I should have written here dia. 1.5 centimeter diameter, 1 meter length, and here hinged at both the ends. No. Instead of that, suppose if I say fixed at one end, free at other. Where you have to make changes?
The length.
Where you have to make changes? So you have to make changes in this effective length. So effective length becomes how much? Effective length becomes how much? 2L. So this becomes like 2L. This becomes like 2 meter. This becomes like 2000. Okay. Now what would be the difference, man? Now what would be the difference? Instead of dividing by 1000 square, if you divide it by 2000 square, so that is like 2000 square is like 2 into 1000 square, so that is like 1 by 4 times less. So then this load would have become like 1 by 4 times less. So that means it would have got like 1250 newtons. Okay, so almost equal to like 125 kgs. So like this, suppose if it was fixed at both the ends, instead of this fixed at one end, free at the other, if it was fixed at both ends, then L would have become what? L by 2, half L. So instead of this 1000 square, so half L means this is how much? 500 mm. 500 mm is as good as saying 1000 divided by 2. So 1000 square, so it is 1000 divided by 1 by 2 square. So 1 by 2 square. So that means what? This 1 by 2 square, this 4 goes up. So that means this should have been like 4 times larger. Okay. So like this, you can use this Euler's equation to solve numericals. So this is a very fundamental equation to solve for long columns. Now the crippling stress with long columns. So you know the 4 conditions here. Please remember the 4 conditions. LE is equal to L for both ends hinged. Both ends hinged means like this. It is free to rotate at the ends, like the door hinge. Pinned or hinged is the same. Pinned and hinged are the same. Guys, please remember. Pinned is equal to hinged. Okay, it makes no difference. Okay. So here you got both ends hinged. Here you got both ends fixed. Here one end hinged. So pin and hinge is same. Okay. So like this, we can solve numericals. The only problem with this formula is that if this becomes like very short, instead of 1 meter length, if it becomes 5 centimeter length, then what would happen? Then you would have a very large value, because you are not dividing by a large value, you are dividing it by a very small value. 5 centimeter is how many meters? 0.05 meters. 0.05 meters square. So this value of PCR would become so large that even a short rod, even with compressive loads, it will not be able to take so much of load. It will become large, too large. So these are not fit for short columns. These are only fit for, this formula is only fit for long columns. So how much long? We will actually see that is actually referring to LE by K ratios, which is actually the slenderness ratios, which depends on the material, whether it is steel or aluminum or copper. Okay, which will actually tell it in the next class. Okay, so this is how you should use the Euler's formula.